Today, we're going to talk about curl and divergence.
So what are they? So I actually look up the name in Chinese. I'm going to also explain that to you in detail. In this section, we're going to define two operations on vector field.
Curl and divergence.
But one produce a vector field and the other one produce a scalar field. The one that produce the vector field is the curl.
And the one produced a scalar field is the divergence.
So let's talk about curl. First of all, we have this vector field F over here. It has three components, P, Q, and R. And the curl of this vector field is defined to be this, right? It looks like a very long expression over here. We're going to have an easy way to remember this curl, the curl of this. Think about the symbolic determinant of this 3x3 matrix. The way we do it here is we're going to put I, J, and K over here. And then this symbol over here, there's like a upside down triangle. It's called del.
It is the vector differential operator.
Do you remember the differential operator we have in one-dimensional calculus? So at that time, that was dx. That was differential operator for one-dimensional calculus. But today, we have this vector differential operator as called del. You can see some similarity between them. Okay, try to relate them and think about that way. So this del over here is defined to be this way. Okay, defined to be this way. So basically, you just take each component and take the partial derivative with it. Okay, for example, in the past, we find this del of f. Okay, at that time that was called the gradient of f. Right, there was a gradient of f. So you can think about it as this differential operator del acting on this function f. So what do we have? We're going to take each component, right? And then the first component differentiate with the partial derivative with respect to x. And the second one, pick the function, and then differentiate with respect to y. And then pick that function and then differentiate with respect to t. Okay. So think about that. That is the vector differential operator. It's called del. Think of the del here as a vector differential operator. Then we can remember this curl of f over here. We can think about that as the symbolic determinant of this 3x3 matrix. The first row here, we're going to have ijk over here. The second row, remember when you do cross product, right? You're going to put this, think about this down here. Okay, you put it over here as a second row. And there's F over here. It has three components, P, Q, and R. And you put that as the last row over here. Now, when you compute this, the determinant of this, remember how we expand this, right? So the way that we did that was, so we take the I, okay, so we take this I, and then we cross out the column and row that contain I, and we end up with this submatrix. And so the determinant of this submatrix is partial derivative of this R with respect to Y, so which is this. And then subtracting partial derivative of this Q with respect to Z, which is this, right? So this is how you get this I component, okay? Similarly, for the J over here, remember when you calculate the determinant, the sign of this go plus, minus, plus, okay, when you try to expand that. So this time it's going to be a minus, okay, the J component. And then you cross out the row and column that contain J, and then you take the determinant of the submatrix, so it will be partial derivative of R with respect to X, which is this one. Okay, so I should write it over here. it has a minus sign. So partial duality of R with respect to X, and then minus partial duality of P with respect to Z. And this is for the J component, right? Okay. Now distributing this minus sign here in front, right? You take opposite at every turn, and that should give you this. It's a sum over here, right? And then at last, for the K component, then you cross out this row and this column, and you get the submatrix, and you get partial duality Q with respect to X, which is this, subtracting partial duality of P with respect to Y, which is this, right? So this is called the curl of F, okay? You can think about, this is the del, the cross product of del with F, okay? So curl is the cross product of del and F. Now, some people will say, oh, what happened if the vector field, the vector here is
only have two components, P and Q.
so what will be the curl of this vector field? Anybody? Anyone? What do we do when you have only two components? What happened to the third component? Equal to 0. Yeah, very good. So if this R over here equal to 0, okay, then when you expand it this way, then what happened is the result here, okay, try that at home. You can try that. So the result here, can you guys try that? If this is 0, think about if this is 0, and what do you get? Okay, I'm going to pause here and let you work on it. So anybody tell me what you get? Yes, very good. So now try that. This one I get the biggest screen, but however, it's a little bit slower, okay? So you get this, okay? So you get the partial duality, you get this component, right? This is only one, okay, only one right here, okay? This one here actually, does it remind you of Green's theme, right? That was the function you take double integral with, right? Okay, all right, so this is the 2D curve, okay? So when the function has only two components, okay, the P, the I and J component, okay, when the vector field has only two components, when the third component is equal to 0, okay? All right, now let's try some example so we can be more comfortable with curve, okay? So curve over here, we're given this vector field, okay? This one, it has three component function, and we try to find the curl of this function. So we will construct this 3 by 3 matrix. It is the cross product of del with F. What should I put as the second row? That's del, right? Del is the vector differential operator. So that will be partial duality with respect to X, partial duality with respect to Y, partial duality with respect to Z, okay? And then the last row, what should I put there? Yes, then you just put the component function in there, right? So this one here will be xz, and then the second one will be xyz, and then the last one is negative y squared. Oh, okay, negative y squared there. And then you just compute this using the way that I talk about, right? So, and then continue, and then you get this result. Now, most computer algebra system has command that compute curve of a vector field. So you can actually use a computer algebra system to do it. You should actually try to do it by hand first, and then you can check your answer using maybe some computer system, maybe a graphing calculator or some other system, but do it by hand first. I actually have some picture over here, curve. Okay, so what is this curve? Now we know that curve is this curve of this vector field is going to be del cos of this F, right? Cos with that. So in physics, the meaning for this I put it over here. So I want to give it the idea of what's curve first before we move on. I actually have the Chinese translation also. Roughly speaking, the curve measures the tendency of the fluid to swirl around the point. So, for example, think about the water is flowing through this. Okay, so at any given point over here, so suppose this point here is a point in here, and the curve is pointing this way, and it measures the tendency of the water swell around this point. That is curve.
The magnitude of this curve is a measure of how quickly the particles move around the axis.
And then the direction is going this way. So it will swell around this way, then the direction of that curve go this way. Here is actually a paddle wheel to measure the spring. So suppose this is water, and you put this paddle wheel here, and you can see that the paddle wheel, if it's spring, okay, and then it's going to measure how fast it's spring. We can tell the curve, okay. So this is using paddle wheel to measure the spring, and you can tell the curve. Okay, so curve measure the tendency to swell around a point. Now we call that the gradient function of three variable is a vector field on R3. Remember when you take gradient, right? When you take gradient of a function, again, this is going to have three components: partial derivative with respect to x, with respect to y, with respect to z, right? So the gradient of a function f, which is, I'm going to put it right here. The gradient of the function again, is going to be a vector field, right? It's a vector field on R3. Remember, it has three components, right?
Partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z.
So it is a vector field on R3. And when it is a vector field on R3, we can also compute the curve of it, okay? This theme over here says that if you have the gradient of a function, and this function has continuous second order partial derivative, okay, which means that if you take second order partial derivative, they're all continuous, okay? And then you compute the curve of that. The result here turned out to be magically zero, okay? And why? Why is that zero? And we have a proof of this. So the proof is like this. So we're going to compute the curve. We're going to construct this 3x3 matrix and find the determinant. And now the third row over here is going to be the gradient of the function. So that's the gradient of the function over here. Now, when you do that, it turned out to be this, okay? And now this and this, when they subtract, actually turn out to be zero. Why? Because the order you take the partial derivative doesn't matter. By what theme? What's the name for the theme? Start with a C. What is the name? Corrosive. Okay. So this and this are equal. The order you take partial derivative here doesn't matter for that function. Okay. And so this one, so they're subtracting and you should get zero. And similar for this and this will become zero. So the curve of a gradient of a function is equal to zero if the second order partial derivative are continuous. Okay, so if the second order partial derivative, they're all continuous, then the curve of the gradient is equal to zero. So that is one interesting result about curve. Now we can actually try to think about the similarity, okay, between this one and A cos A, right? What's A cos A? How do you do cos product? So when you do cos, remember we use right hand, right? A here, and then you cos, but then you don't curl your hand, right? So it's A here and then curl. A cos A is equal to zero. Remember, A cos A is actually the magnitude of this is the area of the parallelogram, right? A here is this, and then A here is this. So there's no parallelogram, right? So the area of that is zero, okay? So A cos A is equal to zero, okay? A cos A is equal to 0, the 0 factor, okay? Now this one here is kind of like this, okay? There's a similarity, okay?
Del cos with del of f is equal to the 0 vector.
You can try to see the similarity between this one and this one. All right, so since a conservative vector field is one for which that the big F function is equal to the gradient of some small scalar function f, right? Remember in 16.3, that was a video I made, okay? And at that time, we talked about the conservative vector field. If you don't remember, now you remember. So what does it mean, a conservative vector field? It's one that the f here is equal to the gradient of some small f over there, okay? So if f can be written as the gradient of small f, then f here is a conservative vector field, okay? To remember this, try to think about duality and anti-duality, okay? So, for example, in the past, f here is equal to gradient of this f, okay? Now, for this, let's try to think about this. So you have this big F function that is the duality of the small f function, okay? In one-dimensional calculus, say we have a function that's the duality of the small f function, then this is anti-duality of this function, right? Now, for this vector field f over here, that's equal to the del of f, which is gradient of f, okay? So this kind of play a similar role as this one over here. So you try to compare them, okay? The small f here is kind of like the anti-duality of this over here. So you see the relation. Okay, so if big F here can be written as the del of small f, then the big F here is a conservative vector field. And if the big F here is conservative, then what happened to the curl of F? According to the theorem above. So what does it mean is conservative? That means, that means this F over here is equal to what? Del of F, right? So the big F is conservative, which means that it can be written as del of F, okay? Gradient of F, okay? Then by the theorem above that we just proved, what is the curl of this? What's the curl of gradient of F? What does it equal to? That's equal to 0, right? Okay. So yes, that's equal to 0. So if the vector field is conservative, then the curl of it is equal to 0. Okay, the 0 vector. Okay. Now remember, this gives you a way to verify if a vector field is not conservative, because remember the statement and the contrapositive statement are equivalent, right? So if A, then B, then the contrapositive statement of this is going to be if what? If not B, then not A, right? And these two statements are equivalent, okay? A statement and its contrapositive statement are equivalent. Sometimes if the statement is hard to prove, you can try to prove the contrapositive statement, okay? So now, if the curl is not 0, it's not the 0 vector, then that F here is not a conservative vector field. So this is going to give you a way to prove the vector field is not conservative. Okay, question? All right. So here there's a note over here. Is try to compare this with this exercise 29, 16.3. At that time, we tried to show that this vector field is conservative. That if it's conservative, what happened? If it's conservative, then we will have the partial duality will be equal in this 3 way. Okay, all of this has to be satisfied. Okay, so now you see that there are 2 ways to show vector field are not conservative. One way is try to show that the curl is not zero. Okay. Another way is try to show that one of this does not satisfy. Then the vector field is not conservative. Okay. So two different ways to show a vector field is not conservative. Okay, now let's try more example so we can be more comfortable with curl. Here's an example to use that, okay? We're trying to show that this vector field is not conservative. So we're going to use the first way. We're going to try to show that the curl here is not equal to zero, right? And to calculate the curl, we're going to construct remember the determinant, right? Do it that way. And then it turned out to be this. Does it equal to zero? Well, it is not zero, right? The component here, it is not zero. So then the curl of this is not zero. Okay, so we know that this is not zero. Okay, so by the theorem above, right, if the curl is not zero, then the vector field is not conservative. Now, the converse of this theorem over here is not true in general, okay? So what's the converse? Converse is just go backward this way. It's not contrapositive, it's just go backward. So what's converse? Okay, so suppose you want to know. So that is converse, okay? So if A, then B, the converse is if B, then A. Just reverse it. That's the converse. Okay. The converse is if B then A. So the converse of this is if the curl is equal to zero, then the vector field is conservative. That's not true in general. But if we what happened? But if the vector field is defined everywhere, that is actually true. Okay, suppose the vector field is defined everywhere, okay, or more generally, if the domain is simply connected. So what do we mean simply connected? Say this one over here is simply connected. This three over here are not simply connected. For example, if you can find any 2 points over here, then draw the line, and some point over here is going to be outside the region that is not simply connected. Okay, so if the vector field is defined everywhere, for example, defined on all R2 or R3, and then or defined on simply connected region, something like this, then the converse of this is going to be true, which means if the curl equals zero, then the vector field is conservative. Okay, so here's the thing. So if the big F here, this vector field is defined of all of R3. Okay, so it's defined everywhere. Okay, whose component function has continued partial duality, and the curl is equal to zero, which is curl equal to zero over here, then the vector field is going to be conservative. Okay, all right. So on R3, if the vector field is defined on all of R3, then the converse of this is going to be true. Let's try to use this example to show this. Okay, we have this vector field here. Okay, we're trying to show that this is a conservative vector field. First of all, let's think about this. Is this vector field here defined on all of R3? Is it defined on all R3? Yes or not? Yes, because this is all polynomial, right? They're all defined. There's no discontinuity, right? There's no X and Y or Z to make this undefined, right? So that is defined on all R3. Okay. Now by the theme above, if it's defined on all R3, okay, and each component function has continued partial duality, and looks like it should be because each one polynomial function certainly has continued partial duality, right? So the next thing we want to do is we're trying to show that the curl equal to zero. Okay, so we're going to compute the curl. To compute the curl, remember we do this determinant of this 3x3 matrix, right? So again, let's just review this. What should I put as the second row? Partial duality of the operators, right? Okay, so that will be those operator right here. Okay, and what should I put as the last row here? The component of F, right? So we're gonna have this, and we'll put it here. This, put it, oops. And then this one here, we put it here, and then this, we put it over here. Now, when you do the computation, it turned out to be 0, okay? The calculation, you can verify that. So it turned out to be 0, okay? It's a 0 vector. See the ball face 0 here, it means it's a vector. So the curl of this F here is equal to 0. If the curl equal to 0, okay, remember, and the domain of the function is all R3, right? It's defined on all R3. So F is a conservative vector field by the theme that we just mentioned. The second part over here, we're trying to find the function. Now we know that the big F here is conservative, right? So which means that it is the gradient of some small f function. Now, how can I find that small f function? What should I do? Given that big F equals this. It's kind of like, if you know the duality, how can you find anti-duality? It's a similar idea. You take anti-duality, right? You integrate, yes, right? Okay, so we have this function over here. Because the big F here is the gradient of small f. So this one here should be the partial duality of f with respect to x, right? Okay, or another way to put that, maybe I should just put fx. This one here will be partial duality of small f with respect to y, and this should be partial duality of small f with respect to z, right? Okay, because the big F here is the gradient of small f. So each component will be the partial duality of f with respect to x or y or z. Okay, so now we're going to fill in the blank over here. So partial duality, so what should I put over here? This first one, that should be what? Partial duality of small f with respect to x is what? Yes. So that's y squared z cubed. And the second one here is 2xy z cubed. And then the last one is 3xy squared z squared. And as you said that, well, it's just like you take anti-duality. We're going to do integration, right? So we're going to integrate with, the first one here was partial duality with respect to x, right? So we're going to integrate with respect to x, okay, with respect to x. And what do you think we're going to get here? What's the anti-duality this with respect to x? Does it have any x here? No x? So you can think about kind of like the constant, right? So you have this constant multiplied with, multiplied with x, right? Isn't it? Right? So you're going to get the x over here, x, and then multiply with y squared z cubed, then you get this one. However, that's not all. Okay, that's not all. What else here? When you integrate with respect to x, then the function over here, remember in the past, when we take anti-duality, we press a constant, right? We add a constant. So the constant over here is actually with respect to x. So this one here, it has no x over here. So this is kind of like the constant that you put when you take anti-duality. So you add a function that has no x in it. It is like a constant function with respect to x. Okay, so you have this one here. So it's a function that depends only on y and z. It should have no x. So you find anti-derivative this with respect to x, which is this, and then you add a constant function with respect to x. So it's a g of y and z. All right, so after this, what should we do? We try to find this small f function, right? So we're going to start from this. Because we know the partial derivative of the function with respect to y,
we're going to take the partial derivative of this function f with respect to y, and then compare that to find out what this function g is equal to.
So we're going to differentiate this with respect to y. What's the derivative of this with respect to y? 2x, y, dq, you got it. And what's the derivative of this with respect to y? Here have two variables. So we should say partial derivative, to be strict, to be more precise, okay? So it contains two variables, so we should say partial derivative that with respect to y. So that will be partial derivative this with respect to y. Then we'll get this one over here. Now let's compare this one with this one. What can we say about partial derivative g with respect to y? What does it equal to? Comparing this with this one. That should be equal to 0, right? See, this one here equal to this. And this one here, these two match. So this part over here should be equal to 0. Then should be equal to 0. All right, so if that equal to 0, so what does it mean the partial derivative of g with respect to y equals 0? That means the g over here is going to be like a constant with respect to y, right? So if it equals 0, that means g is independent of y. So it should have no y in it. So it's independent y. So therefore, it should be just a function of z only. It is a function of z only. Okay. Now, if we write it as a function of z only, right? Then you can actually replace this by h of z. This is the same as this. So, okay. Now,
Remember that we haven't made use of this last equation about the partial derivative of f with respect to z.
So let's differentiate this with respect to z. Then you get xy squared. The derivative of zq is 3z squared. So that's the derivative of this with respect to z. And then remember this part here become h of z, right? Equal to h of z. So the derivative of that with respect to z is going to be h prime of z. So we get this one over here. Now, if you compare this one here with this one, what can you say about h prime of z? That should be equal to 0, right? Okay, so that will equal to 0. So h prime of z equals 0, which means that, what can you say about that function? What kind of function you get? It's a function of one single variable, right? So it is going to be a constant function, okay? So when the derivative of a function of a single variable equals 0, then it is a constant function. So that means from here, that means h of z here is equal to a constant. Let's call that c or k, okay? Now after that, then you can put it back, okay? So put this one over here, is this, you put it over here. So therefore, we put all the information back together. Oh, they use k instead of using z. So I'm gonna just use k to go with it. So it's this k over here. So the small f function will be xy squared eq, and then that is going to equal this, and that equal to k. Okay, so that's how we got the small f over here. The idea is kind of like taking antiderivative, right? And then we compare them, okay? Try to figure out this right here, okay? All right. I'm going to ask someone to read this paragraph.
The reason for the name curve is that the curve vector is associated with rotations. One connection is explained in exercise number 37. Another occurs when the big F, the vector field, represents the velocity field in fluid flow. Particles near XYZ in the fluid tend to rotate about the axis that points in the direction of the curl of f, and the length of this curl vector is a measure of how quickly the particles move around the axis. If the curl of f is equal to the zero vector at a point P, then the fluid is free from rotation at P, and the vector field F is called irrational at P. In other words, there's no whirlpool or eddy at P. If curl of the vector field F is equal to the zero vector, then a tiny paddle wheel moves with the fluid, but doesn't rotate about its axis. If the curl of F is not equal to the zero vector, the paddle wheel rotates about its axis. We give a more detailed explanation in section 16.8 as a consequence of Stokes' theorem.
Okay, roughly speaking, curl measure the tendency of the fluid to swell around the point. Curl itself is, I'm going to ask you, is it a scalar or a vector? Huh? It's a vector. Curl is a vector, okay? So it has direction and also magnitude, okay?